You're going to do some pre-lab work. The pre-lab work has to do with your notebook. And so your lab notebook, which is the quad-ruled sewn binding thing, and if you can't find quad-ruled, just regular line paper is fine. But on the cover, you know, just write your name. Make sure it's there. In case you forget it. Now for page one, leave it blank. You know, we're going to use page one as a table of contents. We should only need one page for this. If you make a mistake, we don't tear out the sheets. Let's say you already wrote on page one, no big deal. You know, if it's not important, just cross it out with a big X. Right? But never tear out any pages. This is why I'm requesting a sewn bound notebook rather than spiral bound or something like that. You're not meant to tear out any pages. It's supposed to be a permanent record, you know, of the experiment. And so it's sewn bound so I can easily see if you tore out pages or not. And so just leave this blank. Now most people will write just on one side of the page, and that should be no problem. We should have plenty of pages for this semester, so you could just write on one side rather than on both sides. But it's up to you. All right, so when we go to page two, we need some kind of lab title. The title for this lab is going to be Synthesis of a Chromium Complex. So you need to read through the experiment and prepare your lab notebook. There's actually a synthesis of a chromium complex, synthesis of aluminum complex, synthesis of a copper complex. We're not going to do all of them. We're only going to do synthesis of a chromium complex. You know, I like chromium because we do redox, acid-base, and metathesis in this reaction series or this experiment. Aluminum, we would do redox, actually.
You can only write pen in the notebook?
In the notebook, only pen. If you make a mistake in your notebook, you just exit out or something like that. You don't make it non-legible, because if you did something like this in your notebook, people are going to suspect, you know, what's under that. They're going to start to question that. The notebook is supposed to be some sort of legal document, legal record of your experiment. But don't worry if your notebook gets messy, you know, with all these X's and corrections and whatever else. If you have to write in ink, well, that's one of the prices you pay. Nobody expects their notebook to be nice and pretty. The people who have nice and pretty notebooks probably aren't working that hard. You know, if you go into a laboratory and you look at people's lab research notebook, you know, water spills, coffee spills, chemical spills, you know, just a mess, sloppy writing. You know, some people will be neat. So the lab notebook should be complete, you know, but it doesn't have to be neat, and you aren't graded on neatness. Unfortunately, a lot of people have this mixed up, because when I look at some people's notebooks, they're just very nice, very well organized. But when they turn in the reports look awful, because what they did was they collected all their data on the report, right, on the report sheet, and made all the mistakes there so that they could keep their notebook nice. But what they're turning in to me to get graded is their report, not their notebook. And so they have it backwards. And so in other words, reports can be done in pencil. You know, do you know why you don't use pencil for notebooks? Anybody have an idea? Because in like a couple of years or 5 years, it's faded. You can barely see it, right? It's not permanent. If a report, you know, if you wrote it in pencil and it fades, you can always generate a new report, right, if you have your original data. We're guilty because, you know, Chem 4, Chem 1A here, what you do is you write your original data on the report and you turn in the report, right? That's bad. You never write your original data to give away to somebody. What if they lose it? If they lose it, then you have no permanent record that you ever did the experiment. And so if you give a report away with the original data, you better make a copy or give them a copy of the report. Reports are always meant to be given away. You know, when somebody requests a report, you don't say, well, you know, I'd like that report back. You just give them away. You just make extra copies, right? And so what we're going to do is we're going to put all our original data in our notebook so that we have this always. And the reports, well, we can always generate those or write new ones or do whatever. And so all this will be done in ink. So what you have to have done before lab is the title and the procedure. The procedure, you don't want to rewrite the written procedure in the lab manual. What you want to do is you want to make it, you know, more compact and easier to perform. And that is, you know, if you write a whole bunch of sentences or paragraphs, then it's slow going. And so what I like to do is I like just to draw little pictures. So for example, we need to add 3.6 grams of potassium dichromate slowly into, let's say, a beaker. This beaker is going to contain a suspension of 10 grams of oxalic acid and 20 milliliters of water. And so I'll just take the first part of the experiment and then just write it like this. And that way, when I go into lab, I don't have to write that much. You know, in research labs, you know, you're busy, you're doing the experiment, you don't want to write that much. And so this is really important to do this pre-prep because sometimes what happens, and this has happened to me, is I don't prep the lab and I end up writing observations, but I end up writing minimal observations. So one time I performed an experiment. It took, I think, a month or two. And then a couple of years later, I wanted to write it up. You know? And so I went back through my notebook, and I couldn't figure out what I did. I was missing some key bits of information. And so what I had to do is I had to redo that experiment. And so it delayed things by a couple of months. I was redoing all that data collection. And so here we just want completeness. And so the procedure is what you're supposed to do. Your observations are what you actually did, and in addition to what it looked like. And so, for example, here it says 3.6 grams. You probably don't weigh it. You know, it's too much hassle, you know, getting exactly 3.6 grams. You probably got something like 3.615. Actually, we aren't going to use that precise. We're just going to use a centigram balance. So we might have gotten 3.61 grams. Are you going to scrape out some crystals, or is that close enough? That's close enough. You know, this is a synthesis experiment. And so that's close enough. And so what we say is 3.61 grams of potassium dichromate. Does everybody know what potassium dichromate looks like? Does everybody know the color? You know, if everybody knew what it looks like and what color it is, then you don't have to write it down. Like, for example, HCl, everybody knows it's colorless, you know, aqueous. But for something like this, we better write it down. Potassium dichromate, the stuff we get, is an orange powder. You know, it's a finely divided powder like flour, you know. And for the oxalic acid, which I abbreviated to oxac, maybe we got 9.85 grams of oxalic acid. And the 20 mils, do we have to get that so precise? No. You know, just approximately 20 mils of H2O. And so for our observations, this is what we write. But it says slowly added. If they're asking us to slowly add it, then maybe it's potentially violent, right? It is. One semester I had a student just dump it in, and it just went all over the lab bench, and they were shocked because they didn't know, you know, why did it do that? Well, did you read the instructions? No, they just dumped it in all at once. And the reason is potassium dichromate is a powerful, what? Yeah, potassium dichromate is a powerful oxidizer. And so what's the reducer here? Potassium dichromate is a powerful oxidizer. The reducer is actually oxalic acid. Is oxalic acid a good reducer? And so let's take a look at the oxidation states of oxalic acid quickly. plus 1, minus 2, it's plus 3. Plus 3, carbon in the plus 3, I don't expect to be a reducer. I think that this is electron poor. I would think oxalic acid is more of an oxidizer than a reducer, right? But in this case, what we're going to do is we're going to mix a powerful oxidizer with a really bad reducer. And that means we don't have to use an explosion shield, right? We can do this on the lab bench, but you still have to be careful because you don't want it to splatter everywhere, right? Well, is that the only hazard? Well, you know, what I want you to do in your pre-lab is I want you to take a look at the MSDSs. You know what MSDS stands for? MSDS stands for Material Safety Data Sheet. Do you see this little diamond or whatever? Do you recognize that? There are 4 things. Blue is health, red is fire, yellow is reactivity, and then the white is the personal protection. If you see 4s there, be careful. A lot of 4s, that's dangerous stuff. And so when you walk by doors, you know, you go to UCLA or something, you walk by a door, it's all 4s. You know, that's like get away from that area. You know, don't hang around there because something bad might happen. It's like being in an avalanche zone or something like that. Stay away. But we have a 4 there. The 4 is for health. So watch out for this stuff. And so, you know, there are lots of people who don't read. You know, they go over the balance there, and it's like fluffy flour. And so some people are pouring the potassium dichromate and creating a cloud of dust. And this cloud of dust, orange dust, you know, people are inhaling, including the student making the dust cloud, right? And so, you know, that's happened to me many times. You know, aerosol of potassium dichromate's gone around. And so what I'm doing now is I'm putting the balances inside the hood. So at least if you create some dust, it's going to get sucked out into the hood, right? Rather than inhaling it. Because what exactly are the hazards of potassium dichromate? And so you can read about the hazards of potassium dichromate. You know, it's nasty stuff. You know, it's a powerful oxidizer, of course, so it's going to irritate everything, including this. It's a carcinogen. It's classified A1, confirmed for humans, carcinogen. Do you want some, you know, would you feel comfortable if you're standing behind the person making a dust cloud of potassium dichromate? It's happened. It's happened. You know, what do you think that person making that dust cloud of potassium dichromate's thinking? Well, I'm going to kill everybody in the lab? Maybe, but they probably aren't thinking because they probably don't care and they never read anything anyway, or read anything anyway, right? Well, that person has got to be booted out of the lab, otherwise they're going to poison everybody else. But this, we got to watch out. Mutagens, you know, cause defects. Tetragens with birth defect not available. Developmental toxicity for kids not available. We don't want to expose ourselves to this, do we? No, not at all. You know, sometimes I hear about carcinogens in the news, like at Porter Ranch, they have that methane leak, and they detected benzene in the methane leak. Benzene is a very interesting chemical because benzene used to be a very popular organic solvent. People used to use benzene for everything, and then all of a sudden it was banned. Nobody could use benzene in the labs anymore. Only for synthesis they could use it, or only under certain conditions they could use it because the state found out it's a, you know, carcinogen. They didn't know it was a carcinogen before. And then I hear, well, there should be no ill effects, right? And so I thought, well, how ironic. Now it's okay, but then back then it wasn't okay, right? But it depends on the level of exposure because everybody's exposed to, well, I think everybody's exposed to carcinogens. You know, if you touch leather, you know, where they use chromate all the time? In tanning leather, right? So if you touch leather, you've already exposed yourself to chromate, correct? Unless they use other stuff. Somebody can update my information. Or gasoline, when you fill up your tank with gasoline, well, you're going to expose yourself to a little bit of benzene because, you know, it's one of the components, right? a certain extent. And so what we got to do is, you know, or if you're at the barbecue, you know, if you're at the barbecue, you eat barbecue food. The American Cancer Society has recommended stop eating barbecued food because it's carcinogenic, right? And so it's kind of hard. In fact, we have to make judgment calls about this. But the thing we do, you know, even oxalic acid, you read about oxalic acid. The thing we have to do is gauge the risk. Now, if there's a risk, we can minimize that risk. The way we minimize that risk is avoid contact, avoid creating dust cloud. You know, if we follow these lab protocols, we should be okay, you know. Usually this carcinogenic effect is, this is a chromium-6. You know, there's chromium-6 contaminated drinking water, and people are drinking it, and there's that whole movie that was made about that. Do you guys remember that? I didn't see it, but it's a very famous environmentalist. But anyway, we have to judge or gauge this risk. And one of these cities in Northern California, I must have looked at this MSDF here. This is a true story. But, you know, dihydrogen monoxide, right? And so DHMO. And so a city up there looks, and then they see that dihydrogen monoxide, this is MSDF. I don't know if I'm sure this is one of these mock MSDSs. But, you know, it's irritant, causes discomfort, causes wrinkling of the skin, can be fatal, right? DHMO. And so the city in Northern California banned DHMO, right? It's a true story. And so what we have to do is everything's toxic to a degree, and so we have to change the way we handle it or change how we expose ourselves to it or minimize our exposure to it, and then it should be okay. But I sent out something about chemical risks so you can make your own judgments, but you know, we deal with carcinogenic materials just by living, you know, and so how we deal with that, we got to think. And so the final word on this is just that in this lab, what we're trying to do is develop skills in which we can handle hazardous materials, explosion hazards, you know, health hazards, all these types of things, safely. All right, any questions on the lab for next week? Okay, we're only doing part for the chromium, and the chromium is a 2-day lab, so we're going to split it. So we're going at the ethanol step, we're going to stop there. What page is it? It's page 79. Oxalate complexes. That's it. Okay. You can name it whatever you want, you know. You can name it its proper name, which is try to name that compound. Does everybody know what DHMO is? Yeah, water. Yeah, you'll need some paper. I have some up here. You don't have any. I'm sorry? Just like 2. You can have some here. I have some extra if you want. Yeah. Are you ready? Any other questions? Not on that. You don't on this. I don't want you to write on the redox chart because I'm going to reuse those over and over again. That doesn't stop people from writing. I already saw some writing and it was wrong what they wrote on there, so don't trust the writing on there. I didn't write it down. Somebody called this the oxidizing agent and it was wrong. It's out there still. I think you'll be able to figure it out though. Because I didn't erase it.
What sections in chapter 24 are you guys going over?
1 through 3.
Okay, so I'll make a worksheet for that.
Okay, I already finished 1 through 3 and started 15. This is the
Erasing.
I'm doing calculation too. Just set the initial here, 2, 1, 0, 0. And then you know what I see here. Yes, fine. I mean, also, I'm just asking what we're trying to get except it's a cubic function. So let's see if we can go with that. No, it's fine. I'm going to start off with a cubic because I want to see how many functions. The x oil is going to get the cubic. So let's see. Well, then I'm going to talk about success in the conservation. And then I'm going to talk about other tricks that we can use to make the math easier. We can find out how many are so we can be able to solve a cubic. No, I wouldn't actually. I wouldn't want to do it. It's too much work. Yeah.
And then successive approximation.
The tricks would be resetting the initial. That would be one. And then the next trick is assuming it's a small. That comes in chapter 16.
Okay, cool.
So, that means for this cubic, we can't do anything except successive.
Cubic.
Because K is one from the other, you can see. So reset or so do successive approximation maybe. And then you don't really have to do X is small because those are in chapter 16. Yeah, and then I'll do the resetting. But I'm going to start again because it helps with some of the problems.
Okay, thank you.
Oh, Raheem.